Now let's just see an example which is related with this concept, and the example says that in the figure ABCD is a parallelogram. So you can see over here that ABCD is a parallelogram. EFCD is nothing but a rectangle. Also AL is perpendicular to DC. We have to prove that area of ABCD is equal to area of EFCD. Furthermore, we have to prove area of ABCD is nothing but is equal to DC into AL. So let's just start with the very first part. So in the very first part, we have to prove that the area of ABCD is actually is equal to the area of EFCD. So first of all, we also know that rectangle is also a parallelogram. Rectangle is also a parallelogram. So if it is a parallelogram, then we can see over here that the rectangle and the parallelogram, they are lying on the same base and in between the same parallels. So if they are lying on the same base and in between the same parallel, then the areas are definitely equal by the theorem. So it implies that rectangle and parallelogram are on the same base and in between the same parallels. It implies the area of ABCD is equal to the area of EFCD by the theorem. By the theorem that we have done now, that whenever we have any two parallelograms that are lying on the same base and in between the same parallels, then by the theorem they are equal in area. So hence we can say that the areas of two are actually is equal to each other. Now let us suppose if I'm just talking about the second particular fact, we have to prove that area of ABCD is actually is equal to DC into AL. So first of all, from the very first part, we know that the area of ABCD is nothing but is equal to area of EFCD, which is nothing but is equal to DC into this should be nothing but is equal to length into breadth, means DC into FC. We can say that because we know that the area of rectangle is equal to length into breadth. So using that concept, we can say that DC is nothing but into FC. DC is into FC. We can say this particular fact. And furthermore, what we have to prove over here, we have to prove that DC, this is nothing but is equal to DC into AL. Now furthermore, if I'm just talking about this particular FC, then we can also write it as nothing but a DC into AL. Why so? Because we know that since AFCL is also a rectangle, it is also a rectangle, then the opposite sides are equal. AFCL is nothing but a rectangle, then their opposite sides are also equal. So it implies that since you can see over here that AFCL is nothing but a rectangle because it is forming up an angle of 90 degrees. So this is also 90, and furthermore this is nothing but a rectangle. So if this is the rectangle, then their opposite sides are equal to each other. It means that in place of FC we can write AL. So we have DC into AL, which is nothing that we have to prove over here. So from this particular example, there is one such thing that we can conclude about the parallelograms, that ABCD is actually a parallelogram whose area is actually nothing but coming out to be is equal to the product of its one side and the altitude. So whenever we are just talking about the area of the parallelogram, so always remember area of a parallelogram is a product of one of its side and the altitude or the height, we can say. or the height we can say. So this is nothing but a concept that we have deducted from this particular example, that the area of the parallelogram is nothing but a product of one of its side and the altitude or the height corresponding to it. So this is all about the example.